Hello class, welcome to this video lecture on calorimetry calculations. In the last video we talked about heat, specific heat, enthalpy change. We talked about endothermic and exothermic reactions. In this video we're going to look at some of the calculations that we can do involving calorimetry. Okay, so in the last video we looked at a coffee cup calorimeter. We talked about how that works and what it's used for. In lab, we're going to be using a calorimeter to determine the specific heat of a metal, okay, among some other things. If we want to determine the specific heat of the metal, we place a hot metal in water at room temperature. Once we do that, there's going to be a transfer of heat. Heat is going to be transferred from the metal to the water. The metal's going to get cooler, the water is going to get hotter until the metal and the water both obtain the same final temperature. We can determine the specific heat by taking masses and temperatures that we measure and do calculations with those. We can plug those into an equation to determine the specific heat. Okay, so let's take a look at that equation. We talked about it in the last video. This is the equation that relates the heat, okay, to the mass, specific heat, and temperature change. Okay, so excuse me, remember we've got the mass of an object, the specific heat of the object, and the temperature change. The temperature change is always T final minus T initial. We talked about the fact that this can be a positive or a negative, depending upon how large or small the final and initial temperatures happen to be. Now, when we take a hot metal and place it in cooler water, there's a transfer of heat. Okay, there's heat flow from the metal to the water. So the heat that the water absorbs is equal to the heat that the metal releases. And so that's what this negative here indicates. The metal is releasing heat to the water. So if we use this equation right here, we can substitute into this equation. Now I'm using a W here to represent water and an M here to represent the metal. Okay, so simply what I'm doing, I'm plugging in for Q, substituting in for Q, the mass of the water, specific heat of the water, temperature change of the water. Over here we can't forget that negative sign. We put the mass of the metal, specific heat of the metal, and the temperature change of the metal. Now, one of the factors that we're going to need in order to work problems such as this is the specific heat of water. Okay, now you will not need to memorize this, but this is the specific heat of water, 4.184 joules per gram per degree Celsius. So that's what we would plug in right here to this equation. Now, when we're doing this experiment in lab, we are going to measure the mass of the water that we put in the calorimeter. We know the specific heat of the water. Okay, we're going to be able to calculate the temperature change of the water. We're going to measure the initial temperature of the water and then the final temperature of the water after we put the hot metal in it. We're going to know the mass of the metal. We're going to mass that. And we will be able to calculate the temperature change of the metal. Okay. And what we're then going to do is after we plug all of these in, we're going to solve for the unknown. So the unknown is going to be the specific heat of the metal. Okay, so let's take a look at an example here with some numbers so you can see how this can be calculated. Okay, so here is a scenario not unlike what we may encounter in the laboratory. An unknown metal with a mass of 92.9 grams was heated to 178 degrees Celsius. The hot metal was then placed into 75 grams of water at 24 degrees Celsius. After 5 minutes, the metal and water obtained a final temperature of 29.7 degrees Celsius. We want to calculate the specific heat of the metal. Okay, so we've got information in this problem very similar to what we will be obtaining in the lab. Okay, so we take the equation that we had on the previous slide and we solve this equation for the specific heat of the metal. Okay, So we've got everything we need in this problem here to substitute or to calculate some of these quantities. Now, recall, let's look at delta T. It's T final minus T initial. So for the water, okay, the initial temperature of the water was 24 degrees Celsius. The final temperature was 29.7. So by doing this subtraction, we can get, the change in temperature of the water. The change in temperature for the metal is going to be the final temperature of the metal, 29.7 degrees. It obtains, the metal and the water obtain the same final temperature. But the initial temperature of the metal was, 178 degrees Celsius. So when we do this subtraction, we're going to get a negative number. Okay? So what we simply do is substitute into this equation the mass of the water. We get that from the problem, 75 grams. The specific heat of water, okay, that was on the previous slide. Okay, that it's always 4.184 joules per gram per degree Celsius. The temperature change of the water, when you calculate the temperature change, you get 5.7 degrees Celsius. Okay, so we can't forget this negative here. The mass of the metal, 92.9 grams is the mass of the metal, and then the temperature change of the metal. Now notice, class, when we do this subtraction, we get a negative temperature change of the metal, so we put that in there. So when you solve this, a negative times a negative, makes a positive, right? So your specific heat should end up being a positive number. If we go through and cancel the units, the grams are going to cancel. Okay, the degrees Celsius are going to cancel, and look what we end up with. We end up with units of joules over grams times degrees Celsius. And what we get for this particular answer for the specific heat of the metal, we get 0.13 joules per gram per degree Celsius. Okay, so we want to make sure that we substitute into the equation, and again, you guys have heard me say this many times, you really need to include the units. Make sure you include the units, because that's a kind of a double check to make sure you've set up the problem correctly. Okay, let's look at an example of calculating the heat of solution. Okay, so here's a scenario, similar to what we may see in the lab. So 6.5 grams of a salt was dissolved with stirring in 45.5 grams of water at 24.6 degrees Celsius in a calorimeter. Okay, so we're taking a salt, an ionic compound, we're dissolving it in water in a calorimeter. After 2 minutes, the solution obtained a final temperature of 29.2 degrees Celsius. We want to calculate the heat of solution, the enthalpy change, and the enthalpy change per gram of solid. Okay, well, we're going to utilize a familiar equation here. The heat is equal to the mass times specific heat times change in temperature. Okay, so we're going to calculate the heat of solution. So we have 45.5 grams of water. Okay, the specific heat of water is 4.184 joules per gram per degree Celsius. The temperature change of the water, it's going to be positive. We take the final temperature, we subtract the initial temperature, we get the temperature change. Okay, let's note the units cancel out here. The grams, the degrees Celsius cancels, and we're left with joules, which is an energy unit. Okay, we're going to take 2 sig figs because of this number right here. So we get 8.88 times 10 to the second joules. Okay, that is the heat of solution. Now, to determine the enthalpy change, we take the negative of the heat of the solution. In other words, we change the sign for this. Okay, so if we change the sign, we get a delta H, an enthalpy change of negative 8.8 times 10 to the second joules. Now, remember, class, from the previous video, if we have a delta H that is less than 0, if it's negative, that's exothermic. Okay, that's an exothermic process. So let's look back at this problem. We've got some water. We dissolve an ionic compound in it And what happens to the temperature of the water? It goes up. Okay? So this salt released heat to the water, and the temperature of the water went up. So that solution process, forming a solution, that was exothermic. Okay? That's an exothermic process. Now, if we want to determine the enthalpy change per gram of solid, okay, if 6.5 grams, if dissolving 6.5 grams of this salt released 8.8 times 10 to the second joules, then how many joules would be released per gram of salt? Well, we simply take the enthalpy change and we divide it by the amount of salt that we dissolved to determine 1.4 times 10 to the second joules per gram. Okay, that's how much energy was released. That's how much heat was released from the salt to the solution. Okay, the solution absorbed, the water absorbed the heat. Okay, so it's negative. That's an exothermic process. So you simply take your delta H, whatever that happens to be, and you divide it by the mass of the salt that you dissolved. And that tells you how many joules per gram were released in this case, or might be absorbed. Okay, so this is how you work through a heat of solution example. Okay, so we're going to look at one more type of example, and this is something that we're going to see in the lab. So the last process was a physical process, right? Dissolving a salt in water to make a solution. That's a physical process. It's not a chemical reaction. Here we're going to look at a reaction. Some reactions release heat, some reactions absorb heat. Okay, so let's look at a typical type of problem here. When 40 milliliters of 1.0 molar HCl solution and 40 milliliters of 1.0 molar sodium hydroxide solution, both at 22 degrees Celsius, are added to a coffee cup calorimeter, the temperature of the reaction mixture reaches a maximum of 27.6 degrees Celsius. How much heat is produced by this reaction? Assume the total mass of the solution is 80.0 grams. Okay, so class, we're going to learn about compounds. So these are compounds. As it turns out, this is an acid. This is a compound called hydrochloric acid. We're going to learn how to write, and name compounds. This is sodium hydroxide. This is a base. And so basically we're taking a solution of acid, we're adding it to a solution of base in a calorimeter, and what happens to the temperature? It goes up. Okay, so what? Heat is being released, isn't it, in this reaction? Okay, so what we want to do, we want to determine the heat produced by this reaction. So the delta H, that's equal to the heat of the reaction. That's equal to the negative heat of the solution. Okay, negative heat of the solution. So what we're going to do, let's calculate the heat of the solution, just like we did in the previous problem. We've got the mass times specific heat times temperature change. Okay, we are assuming when we mix both of these together, we're assuming the total mass is 80 grams. So that's the mass of the solution. Our solvent is water here. The specific heat of water is 4.184 joules per gram per degree Celsius. Delta T, okay, the temperature went up, 5.6 degrees Celsius. So if we cancel out the grams, cancel out the degrees Celsius, we're left with joules, which is what we want. That's an energy unit. When we multiply these, we get 1.9 times 10 to the third joules. Okay, that is the heat of solution. Now, the delta H, that is the heat of the reaction. Remember, delta H is the heat of the reaction at a constant pressure. What do? We take the negative of the heat of solution. Okay, so we take the negative of this, we multiply it by -1. What do we end up with? We end up with a negative enthalpy change. What does that indicate? That indicates an exothermic reaction, doesn't it? So by mixing this acid with this base, the temperature went up. Why? It was an exothermic reaction, and this is the amount of heat that was produced by that reaction. Okay, so class, read over the calorimetry lab, the specific heat enthalpy change lab. These calculations, these examples that I've shown here in this video, we're going to be doing very similar types of calculations in lab. Okay, so hopefully this will help when we get to that particular lab. Okay, I hope you have found this to be helpful. If you need to, watch this again, go over the calculations. It's real important that you understand how to substitute into these equations and solve for these values. Okay.